Hi all, today we will study memory errors. There are two types of memory errors, one is hard error and the other one is soft error. So what is hard error? In the hard error, the chip will be broken, that is it could be a manufacturing defect also. You might have seen your mobile phones, you are putting your memory sticks, right? So the memory chip itself would have been broken or it could be a manufacturing defect. So such kind of errors are called as hard errors. Then what about the soft errors? In soft errors, the stored data will be corrupted, but the cell still works. So the memory cell will be still working, but the data which is stored in the memory cell will be corrupted. So that's why there are two types of memory errors. One is hard error and the second one is soft error. The frequency of occurrence of soft error rate is more. Then in a memory, when there is an error, how do we detect? So detection of the errors in the memory, one way is using the parity. So how do we do that? So what we are going to do is add an parity bit in the each location of the data. On right axis, compute the data parity and store with the data. And on read axis, check the parity, take the exception on the error. So if the parity doesn't match, then we say that there is an error in the read data. So this is one way of detecting an error using the parity. But if you can see there, if you could tell which bit is flipped, that means in a memory, if there is an error in any of the bit, that is if a 0 is being written as 1 or 1 being written as 0, if you could identify what is the error, then what we can do is, so if we could tell which bit is flipped, correct by flipping it back. That means what? If 0 has become 1, what we can do is we can again flip it back to 1. So we are going to correct it by flipping it back and then write back to the same memory location. So after flipping back, we will write back to the same memory location. So this is very advantageous, right? So we have identified the error in the memory also and we are going to detect and correct it. But this we cannot do with the parity. So with the parity, what we can do is we can only detect the error. So we can only detect the error by checking the parity, but we cannot correct it. So then how we are going to correct the error in the memory? So the best way is there are different error correcting codes. So in this error correcting codes, Hamming code is the best one. So Hamming code allows identification of the flipped bit. For example, for a single bit error, that means in a bit stream, if we are testing only one bit, one single bit if error is there, then for a single bit error correction of an n bit word. So if our data is n bit word data if we have, so n bit word, we need log n to the base 2 plus 1 extra bits. For example, if our data bit is 8 bit word data is there, that is D1 to D8, we need 4 check bits giving total of 12 bits. How 4 check bits? Log 8 to the base 2 is equal to how much? 3 plus 1 extra bit, that is equal to 4. That's why 4 check bits. So our data bit here n is 8 in our example. That's why log 8 to the base n is 3 plus 1, that is equal to 4. That's why along with 8 data bit words, we need 4 check bits. So total giving how many bits for us? 12 bits. So the 12 bit ECC code will be E1 to E12. Okay, so now you are clear. So you can see here we have an 8 bit data, then this is the 12 bit ECC. So in this what we are going to do is E1, E2, E4 and E8. You can check there 1, 2, 4, 8 will be the check bits in that 12 bit word and the rest will be data. So the ECC bit whose indices are powers of 2 are used as the check bits. So you can see E1, E2, E4 and E8 will be the check bits and the remaining will be the ECC bits are the data bits in order. So you can see there we have D1, D1, D2, D3, D4, D5, D6 and D7. So what you are observing here, E1, E2, E4 and E8 are there. These will be our check bits. And what about the remaining bits? The D1 goes into E3, then D2 goes into E5, D3 goes into E6, D4 into E7, D5 to E9, D6 to E10, D7 to E11, D8 to E12. So thus we are going to fill the 12-bit ECC. But still you can check the gray boxes here, that is E1, E2, E4 and E8 are not yet being filled. So what data to be filled in E1, E2, E4 and E8 check bits we will see in the next slide. So now you can observe here. So D1 to D8 are there and E1 to E12 are there. So how do we compute E1, E2, E4 and E8? You look at the table here. What is being done? First I have written for E1, E2, E4 and E8 and the remaining bits are E3, E5, E6. Remaining bits are E3, E5, E6, E7, E9, E10, E11 and E12. So what we can do? So total 12 are there. So 12 combinations. So how many bits we read? So 12 combinations. We need 4 bits to represent them. So that's why. So you can observe here E1, 1 is what? 0001. 2 is 0010. Then 4 is 0100. 8 is 100. Similarly, next I am going to copy the other bits, that is 3, 5, 6, 7, 9, 10, 11 and 12. 3 is 0011. 5 is 01101. Then 6 is 0110. 7 is 0111. 9 is 1001. 10 is 1010, 11 is 1011 and 12 is 1100. So like this the table is created. Then next how we are going to fill for E1? You can observe here E1 is E3 XORed with E5, E7, E9 and E11. So now check at the first column, that is E1 line, first column you check. So in this first column you look at the blue boxes here. So where all it is in the first column, where all it is going high. So you observe that this one is for E3, then next one is for E5, then next one is for E7, then next one is for E9, then next one is for E11. So that's why E1 is E3 XORed with E5, E7, E9 and E11. Next, how do we compute for E2? Now check for the second column. So that is this one, E2. So again check the column where all it's going high. So we observe the high, this one is for E3, then next one is for E6, then next one is for E7, then E10, then E11. So if you observe E2 is E3 XORed with E6, XORed with E7, E10 and E11. Similarly, go to the third column. We are going to do for E4. So E4 is E5 XORed with E6, E7 and E12. We can observe this. E5, E6, E7 and E12. So similarly, we are going to write it for E8. Now come to the fourth column here. So this is E8. Check the boxes where it is going high. So this one, this one, this one and this one, that is 9, 10, 11 and 12. So E8 is XOR of E9, E10, XORed with E11 and E12. So thus we are going to write for E1, E2, E4 and E8. So every data bit is covered by 2 or more check bits, and on write compute the check bits and store with the data. And on read recompute the check bits and XOR with the red check bits. Result is called as a syndrome. This is very important. The result will be called as syndrome. If all the bits are zeros, that indicates there is no error. If the data bit is flipped, covering the bits of the syndrome are 1 equal to binary code of the flipped ECC bit. if the stored check bit is flipped, that bit is syndrome is 1. And on error, unflip the bit and rewrite back to the memory location. So, like this we are going to compute. Now, let us see this with an example. So, the example is compute the 12-bit ECC. So, what we have to do now? We are going to compute the 12-bit ECC word corresponding to the 8-bit data word. Now, the 8-bit data word is being given. We are going to compute the 12-bit ECC. So, what is the solution now? We have already seen in the previous slide. What is that? E1 is XOR of E3, E5, E7, E9 and E11. And what is E3? What will be E3? E3 is D1. So, what will be E3? E3 will be D1. And what is E5? E5 will be D2. And E7 will be D4. E9 will be D5. And E11 will be D7. Right. So, that is why. So, I am already having the data bits now. So, if you see computation of E1 there, E1 is E3 XORed with E5, XORed with E7, XORed with E11, nothing but D1 XORed with D2, XORed with D4, XORed with D5 and D7. So, the first bit is D1 bit and the last bit is D7 bit. So, it is D1 XORing D2, D4, D5 and D7. So, you can see there 1 XORed with 0, 0 and 1. So, finally, you will get as 0. So, that is directly you can say how does the XOR gate works. If odd number of 1s are high, then the output will be high. So, you can see here even number of 1s are there. So, naturally the output will be 0. Now, how do you compute? Now, you similarly compute for E2. So, what is E2 there? E3 XORed with E6, E7, E10 and E11. So, E3 is nothing but our data bit D1. So, D1 XORed with D3, D4, D6 and D7. So, if you put the equivalent data bits here, 1 XORed with 0, 1. So, you see there odd number of 1s are there, naturally the output will be high. So, that is how the XOR gate works. Similarly, you compute for E4. E4 is E5 XORed with E6, XORed with E7, that is nothing but, so E5 is D2, E6 is D3, E7 is D4, E12 is D8. So, when we XOR all this, then I am going to get 0 XORed with 0, XORed with 0, 0, we are going to get it as 0 only. And finally, we are going to compute E8. E8 is what? E9 XORed with E10, E11 and E12. E9 is D5, E10 is D6, E11 is D7, E12 is D8, that is 0 XORed with 1 XORed with 1 XORed with 0. So, even number of 1s are there, that is why the output will be 0. So, thus we are going to write the ECC word there. So, how we are going to write the ECC word? How we are going to write the ECC word? So, if I take an whiteboard here, so how we are going to write the ECC word? So, in this 12 bits, right? What you are going to do? So, whatever the computed new E1 data is there, that's E1, E2, then E3, E4. The rest will be the data bits. Here you are going to stuff D1, D2, D3 like that. So, E1, E2, E3, E4, E5, E6, E7, E8 will come here. So, D3, D4, D5, D6, D7 and finally D8. So, this is going to give you the 12-bit ECC. So, if you can see here, so finally thus the ECC word is our, this will be our E1, this will be our E2, E3 and this will be E3, E4, E5, E6, E7, E8. This will be E8. The remaining bits, all these remaining bits will be the data bits. So, thus we have computed 12-bit ECC, right? Hope you have understood the problem. You are going to practice this once again. Now, we will see the other problem. The example is determine whether there is an error in the ECC word The ECC word given is, this is the ECC word, 12-bit ECC word given, and if so, correct it. So now the ECC word is given. What we have to do? We have to check for the error. If there is an error, we have to correct it. So in this, what we have to do? First, identify the check bits. What are the check bits? This is E1, this will be E2, then E3, this is E4, 5, 6, 7 and 8. This will be E8, right? So totally our check bits are what there? 1, 0, 1, 0. So the 4 check bits are 1, 0, 1, 0. That is E2, E1, E1, E2, E4 and E8. So the check bits are 1, 0, 1, 0 from the given ECC word. The remaining bits are the data bits. So from those data bits, you are going to recompute the new E1, E2, E4 and E8 check bits. So the check bits computed from the data bits of the ECC word are, so what is E1? E1 is XOR of E3, E5, E7, E9 and E11. Nothing but what? Nothing but what? Our data bits, that is D1 XORed with D2, XORed with D4, D5 and D7. So that's why the E1 will be 1 XORed with 0, XORed with 1, XORed with 1. That means how output is 0. So even number of ones are high, so the output is 0. Similarly, calculate for E2. So what is E2? E2 is what? XOR of D1, D3, D4, D6 and D7. So the same thing, that is 1 XORed with 0, 1 XORed with 0 and 1. So you are going to get it as 1. So you can see their odd number of ones are high, so the output is going high. Like that also you can do, or individually also you can XOR the bits and finally you will get the output. Similarly, you calculate for E4. It is 0 XORed with 0 XORed with 1. So the output will be 0. And now calculate E8. So now what you are going to get is as 1. So E8 is 1, E4 is 0, E2 is 1 and E1 is 0. So the syndrome is 1, 0, 1, 1. We are going to write like this. The syndrome is 1, 0, 1, 0. So the syndrome is 1, 0, 1, 0. This is the new check bits computed. Then from the ECC, what check bits we have got? 1, 0, 1, 0. So 1, 0, 1, 0 XORed with 1, 0, 1, 0. So output we are going to get as 0. So previously what we have told in our explanation, if the syndrome is 0, that indicates that there is no error. So that's why what we observe here. So 1, 0, 1, 0 XORed with 1, 0, 1, 0, you are going to get it as 0, 0. Thus there is no error in the ECC word. So whatever the ECC word is there, it is correct. So there are no errors. Now we will see one more problem. This problem also you are going to practice. We will see the other problem now. The same kind, similar kind. Determine whether there is an error in the ECC word. This is the ECC word given, and if so, correct it. Similar kind of problem. Again, what is your first step? We are going to identify the check bits now. What are the check bits? This is E1, this is E2, 3 and this is E4, 5, 6, 7, 8. This is E8. So what will be our check bits? 1, 0, 0, 0 are our check bits, that is E1, E2, E4 and E8. So this is the present check bits. Now what we have to do? Recompute the new check bits using the given data bits. So the check bits computed from the data bits of the ECC word are, first you have to calculate E1. So again, what is from the data bits you have to do? So E1 is E3, E5, E7, E9 and E11 XORing nothing but what? D1, D2, D4, D5 and D7 bits XORed. So if you XOR them, that is 1, 0, 1, 1, 1, 0. So you are going to get it as 1. Similarly, E2. E2 is XORing of E3, E6, E7, E10 and E11. Nothing but what? XORing of D1, D3, D4, D6 and D7. So it is this value you are going to get as 0. Even number of ones are there. The next E4, it is XORing of E5, E6, E7 and E12. Nothing but D2, D3, D4 and D8 XORed. So what you are going to get? This value you are going to get as 1. Then what is E8, E9, E10, E11 and E12? Nothing but our D5, D6, D7, D8 bits will be XORed. So if you XOR that, what we are going to get? So odd number of ones are high, that's why the output is going to high. So this will be E8, E4, E2 and E1. So I need to write it back like this. So the syndrome is what now? 1 1 0 1. So 1 1 0 1 1 0 1 is the syndrome, and from the given ECC the check bits are 1 0 0. So when I XOR 1 1 0 1 and 1 0 0, I am going to get the data as 0 1 0 1. That means it is equal to 5, right? So thus there is an error in the bit E5. So of the red ECC, that bit should be flipped back from 0 to 1. Why from 0 to 1? You check here, this is 1, 2, 3, 4, 5. So if you see the fifth bit, it is a 0. So when there is an error, what I have to do? This 0 bit has to be flipped back to 1. If it would have become 1, if it was earlier 1, then after checking, when I came to know that there is an error, I have to flip it back to 0. So now the bit is 0. So what I have to do? I have to flip back from 0 to 1. So giving the corrected ECC word. So what is the, this will be the corrected ECC word. You can check 1, 2, 3, 4, 5. This fifth bit has been flipped from 0 to 1. So like this, a single bit error is detected as well as corrected using what? Using Hamming codes. So using Hamming code, what we can do is we can detect and correct the single bit. If there is a problem with one single bit, using Hamming code we can do the correction. So hope you have understood the problem. You are going to practice again this problem at home. So what about the multiple error detection then? So using Hamming codes, what we did? Only single bit, one bit detection and correction we did using Hamming codes. If there are multi-bit errors, then what we have to do? What if two bits are flipped? Then the syndrome identifies the wrong bit or is invalid. One extra check bits allows the single error correction and double error detection. So you can check the below table here. This is single bit correction, this is double bit detection. Only two bits there is a problem, it is going to detect, it is not going to correct. So how many? So if you see, the data bits is represented by n here. So if the data bits are 8, for single bit correction we need 4 check bits. For 16 bit we need 5, 532 bits we need 6, 64 bit we need 7, 128 bits we need 8 and 256 bits we need 9. That is for single bit detection and correction, whereas double bit only detection, not correction. So for n bit, for 8 bit data we need 5 check bits. For 8 bit we need 5 check bits, 16 6, 32 7. So like this it goes on. So this table is going to indicate you how many more extra check bits we need for n bit data for single bit correction and double bit detection. So there are other, apart from Hamming code, there are other more elaborate error correction and detection codes that we can use as alternatives to Hamming codes. However, they also add the check bits. See, just we saw an example of 8 bits. So for 8 bits we have to have 4 check bits. So add check bits to the data bits and so require extra storage capacity. So to store additional 4 more bits, you need extra storage capacity and extra circuitry to detect and correct the errors. So they differ in the storage overhead, and the complexity of the additional circuitry is also going to increase, as well as in the number of simultaneous errors they can deal with. So what is the advantage of Hamming codes? See there, since Hamming codes are one of the simplest error correcting codes, they are most often used in applications requiring moderately high reliability, where high reliability is required, we are going to use the Hamming codes such as network server computers. There are more complex ECCs also, error correcting codes are there which are more complex. They are used in specialized high reliable applications such as aerospace, computers and communication systems. So these are the advantages of Hamming codes and how using Hamming codes we are going to detect and correct the single bit. Hope you have understood the session. If any comments are there, you can please comment in the comment box and you can like the page. Thank you.